Hi girls, so we've just done the mind map on fields and heats, and now we're going to look at the second part of the fields and heats topic, which is kind of the mathsy bit of it. There's usually a maths question of relating to something called Hess's Law. So very quickly we're going to go back over what Hess's Law is. So Hess's Law tells us that the heat change in a reaction depends on the initial and the final states, and it's independent of root. Okay, and really what this means is it doesn't matter how you get there, whether you take one step or you take 5 steps, the heat change overall is going to be the same. And we can write this in a mathematical expression like this, where the heat change delta H for the reaction is equal to the sum of the amount of moles of the heat of formation of the products minus the sum of the amount of moles of the heat of formation of the reactants. Now, that might look horrendous, but actually this is very, very straightforward. They will always give you the heat of formation of the reactants and the products, and you calculate delta H, or they give you delta H and leave out one of these and you have to rearrange to calculate that. We're going to do the first type first, a fairly straightforward one. The question I'm going to do is from 2019. This is question 6 from 2019, so we're going to do the second part of that, the mathsy bit. So that now would be a good time to pause this and maybe have a look at that, because what I'm going to show you now is the reaction that they've given us, which is this one here. This is taken directly from the question. And as you can see, what I've done is what I do exactly the same with moles questions. I've written out the information underneath each part of the equation that they've given us. Okay, so these are the heats of formation for the various reagents. So this is for the diethyl lead that's there. Okay, this is the heat of formation for carbon dioxide, minus 393.5. This is the heat of formation for water, and this is the heat of formation for lead oxide. Okay, so these numbers are given to you in the question. It's really important that you do this, that you write out your equation and that you write down each part underneath each bit, for the same reason that we do with moles, that it's very easy to get mixed up. And by doing this, you're minimizing the chance of making a mistake. One thing to be really careful of in this question is minuses and pluses. It's really easy to leave one out or get one wrong. So we got to be careful. So what we're now going to do is we're going to do this calculation, right? So what we're going to take is we're going to take the sum of the heat of formation of the product. So that's this part, okay? And as you can see, we're multiplying the amount of moles of each of the products by their heat of formation. So I'm going to start multiplying each of these by the amount of moles in the equation, and we're going to subtract that then from the heat of formation of the reactants by the amount of moles. So we're going to do that now. I'm going to start with the products. I'll put this down, and I'm going to start with the products. So the first product is carbon dioxide, as you can see. So I'm going to start with carbon dioxide. That's minus 393.5. And I'm multiplying it by the amount of moles of carbon dioxide from my equation, which is 16. So again, that's N in my equation. And remember, it's the sum of these products and the sum of these reactions. So I'm going to add this, hence sum, right, to 20 times 285.8. See that? So now the sum of the heat of formation of water. So 20 times by minus 285.8. And I'm going to add that to the sum of 2 times minus 219.0, which again is given to me in the question. 2 times minus 219.0. And I'm going to subtract the heat of formation of the reactant, which in this case is given to me in the equation, is 2 times 52.7. Again, that's a plus number, so just be careful with that. Right, so that's my equation, and I literally tot that up. Okay, and you can put all of that into your equation if you want, but I'm actually just going to do what's in the brackets separately. Okay, and I get minus 438, this bit here, minus 5,716, this bit here, minus 6,296, that bit there, and finally minus 105.4. Can you see that there? There you go. So again, all into my calculator, and I get minus 12,555.4. Okay? Now, it's important to remember that your heat of reaction is per mole of reagent. So you'll notice from your equation here that we've got 2 moles of tetraethyl lead in our equation. Can you see that? So what we've just calculated is the heat of reaction for 2 moles, but we want the heat of reaction for 1 mole. So we're going to have to divide this number by 2, and we get minus 6,277.7 kilojoules per mole is the heat of reaction for the combustion of tetraethyl lead, like that. All right, so that's pretty straightforward, not too difficult. I suppose the main thing is just to be careful about signs, do it step by step, write it out like I do. I know it seems a bit long and cumbersome, but it means it minimises the chance of you making a mistake. And that's it really. There's one other type which I'm going to do now, which is slightly different to this, but hopefully this helps. Have a go at a couple of questions now on the basis of this and see how you get on. Let me know.